Hi, today we'll be doing a video on a array heap. So we're going to start with a new class called, we're going to need an array binary tree, so we're going to just make a small class here. So I haven't done this code in a while, but I'll be doing the code in intellij, so it shouldn't be too hard. So we'll just make a new class here, and then we'll call it array binary tree. .java array binary tree. We're going to use generics again, so we'll say of generic type T. So we're going to implement a few things and then just do a little doc here. So we'll say, what's up with that? We'll do some doc like that, and we'll say array binary tree implements the binary tree ADT interface using an array. Binary tree ADT, so that class has the we're going to have access to all of these, apparently. Don't think we're going to be using any of those, to be honest. Maybe is empty in size. ToString, I don't think we're going to use any of these iterator methods. This is a pretty quick class, it isn't too long of a class. We're actually making two, so this is going to be the array heap. But in order to do the array heap, I think this is our first array implementation of a tree. That's why we're making this array binary tree class, to just set up everything in an array. Because we're not using a tree node, of course, or any heap nodes or anything, so we're just going to work with that. So we'll say we have this doc here. Above that we'll import util. Do we need util? We'll just import it, maybe for the iterator. So import java.util.star. So here we have public class array binary tree of type T. We'll say implements binary tree ADT of type T, then iterable of type T. So implements binary tree ADT of type T and iterable of type T. So public class array binary tree of type T implements binary tree ADT of type T and iterable of type T. So it's going to say we haven't implemented those methods. That's what the error is. So here we're gonna create a variable private static final int default capacity. So remember, an array has a fixed capacity, unlike a link structure with that, which has a dynamic. It's dynamic, so you can add as needed, add elements as needed. There's no fixed size. So here we'll have some protected variables: protected int count, protected t-array tree. Then we'll say protected int mod count. Then we'll have a constructor here. So it creates an empty binary tree. We'll reference the class name for the constructor array binary tree. We'll set count to point to 0. And we'll say tree. We'll have to cast it to a T array because we can't instantiate an array of type T. So we'll cast a T array to new object. And we'll pass in default capacity for the index. Whoops, capacity. That's it. And below that we'll say creates a binary tree. with the specified element as its root. We'll say at param element, the element which will become the root of the new tree. So this is an overloaded constructor. We'll say public array binary tree takes a t element. Here we'll set count to point to 1, and we'll set tree to point. So our tree is up here. We're just accessing our object reference variable, which is null currently. We'll set tree to point to t array, to new object, pass in default capacity. Then we'll say tree of index 0 points to the element. So in this implementation, we're going to say, well, our tree of index 0 points to the element. So if we're saying, okay, well, so there's a formula for this, by the way. I think I'll add it after. But the tree of index 0 will point to the element. We'll work with that later, don't worry about it. Personally, I think we'll probably instantiate a tree like this anyways. We're going to use this constructor, instantiate our data structure, which is our array binary tree. Actually, it's going to be an array heap. We're going to call super, so we're going to create another class here. I think that's all, to be honest. But implements binary tree ADT. Implements binary tree ADT and iterable of type T. So let me just check my notes here to see if I have I don't believe I have anything other than what we really need, which we already have, I mean, so we'll just go with this for now. We're implementing this interface. When we're extending, I feel like we're forgetting extends, no? Okay, no, we're going to need a lot of stuff actually, so I'm just looking for that file. I don't think we're going to be using all that. So we'll just go down. We'll start with our new class. You just may need a few methods like the size. So actually, excuse me, I may just pull up that that file. This was in my resource files. And I have it right here, just pulling it up. We already did the linked heap. This is the array heap, and this is the array binary tree. Oh, I actually forgot that it needed all that stuff. So I think we're just using a few of those methods. Oh no, this is going to be a huge one. Hopefully not. Hopefully we can skip the iterators, because that's just going to take forever. That's like a few hours in itself. Yeah, so we'll just do a few of the methods here. We have a few more. I apologize for that. I forgot that we haven't made an array binary tree yet, so we're going to have to make this class. So we do have a few more methods here. We're going to expand the capacity. So we're going to need a method to expand the capacity, so we'll say protected void expand capacity. Actually, we'll have some doc here first. We'll just say private method to expand capacity if full. Excuse me. private. It's supposed to be private. I've made it protected, so let's just say protected. We can change it to private if we really need to, but I doubt that. So we'll say protected void expand capacity. Capacity here. We'll say tree points to arrays dot copy of tree, and then we'll pass in tree dot length. Length times 2. So if you have a problem with this method, you're going to need to create another array, another object variable for an array, and then pass it in there. You're going to have to create 2 arrays and copy to the second array if we're not going to be able to see this. That happened to me before. That can happen. For some reason the debugger doesn't work properly with this, the debugger doesn't catch on to the new elements. So you may have to, if anything, you may need to create like a tree too, and copy it, something like that, or like expand tree or something. And then, for example, put like tree 2 points to, and then this line. So if we need to do that, we'll figure it out. Usually, like, it's just trial and error stuff. If something doesn't work, you go back and fix it. That's how coding usually works. So you won't really know that it's not gonna work until you test it later on. So if we have that problem, we can come back. So here we'll return the root element. So the root's going to be in index 0 of the tree. Well, in our heap. Just think of it as a heap because we're just using a heap. But you can make an array tree probably. We're just using it for a heap. So here we'll say return the root element of the tree. Return element stored at the root. I actually don't want to be doing Java right now, I want to be doing C. Just because I'm working on a personal project. Finance project. It's just it's a trading bot. I wanted to code that, but I have to do these videos and stuff. But I will be posting some videos on that soon. So we'll say at return element stored at the root. Then we'll say at throws empty collection exception if the tree is empty. Then we'll say public t get root element. So we're just accessing the root element. That's going to be stored in array index 0. So there's a formula. We'll talk about that in a sec. Just know right now that the root of our heap is always going to be in index 0, and the last node, we won't need a reference to the last node like the linked implementation. Last node is just going to be the last index in the array, so the length -1, something like that. We'll say public t get root element throws empty collection exception. Then we'll say here if is empty, throw new empty collection exception. Then here we'll say array binary tree, return tree. Actually, let's put some brackets there. So we'll say if is empty. It really should be array heap, because I think this class was made to use it to make another tree, but we just made the heap. That's okay, so we'll just say that it's an array binary tree. Some type of array binary tree was empty. Then here all we have to do is just return the tree array of index 0. Done. Below here we're going to check if it's empty. Am I missing methods in this? I hope not. We'll go with this for now. I don't think we use get left and set left. No, because we have a formula to store our nodes. So it's really just an array and we're just storing our nodes. this is just array practice, honestly. It's not even a tree. It's just like, it's thinking of an array as a tree. It's not really a tree. I might as well just give you, so you know, so I don't explain it too late. But I'll just explain where the nodes are going to be stored. So we have the root of the array heap is at index 0. This is for an array heap. This is what we're using our class for, an array heap. I think this class array binary tree was made for an array tree as well, but we're just going to make an array heap. So the root is stored. Where should I put this information? Maybe at the very bottom. What is this? This is our class. Yeah, maybe below here. So we'll say root of array heap is stored at index 0. So here we'll have, so we'll have for each node n, n's left child will be stored in index 2n plus 1, so that's the formula of the array. It's a little confusing at first. I'll explain it in a sec. And we'll say, we'll do the same thing for each node. For each node's n, n's right child will be stored in index. So I think the formula is actually 2 times n plus 1. But if you expand that as like a binomial or something, I forgot about math, but it's like it becomes 2n plus 1 if we like factor it. Sorry, 2n plus 2 of the array. So for example, let's say well, the root's stored at index 0. So say the root's at index 0. We'll say a root is at like index 0, right? So then left, we'll just say left child will be at, we'll plug into the formula. Okay, so we're going to plug into the formula. Where's the left child? So we're going to take this formula here. So we're going to plug in the root for n, right? So 2 times 0 plus 1. That will be equal to, well, 2 times 0 is 0 plus 1 is 1. So the left child of the root, which is index 0, the root's in index 0, and the left child is stored in index 1. There you go. So now, where's the right child stored at? So we'll do right z. We'll say that it's stored in, well, we're going to take the formula directly. Plug in 0 for n, because that's where we're looking for the right child of n, which is the root. So we'll go 2 times 0 plus 2. I'll do it like that. Equals to 2 times 0, which is 0, plus 2, which is index 2. So the opposite of that is also true. There's something else. So we'll say for any node n other than the root. So the root's not going to have any parent, of course. And we'll say n's parent is in index n minus 1 divided by 2. And this is Java dividing, not like just normal dividing. So if you're not sure, like me, you may have to system.out.print like what is n minus 1 divided by 2, and you can put in like 0 for n. Or so okay, so let's say we're finding n other than the root. So for looking at n, any node n other than the root, they're going to take n. Let's say it's 1. Then we'll say 1's parent is in index 1 minus 1, which is 0, divided by 2. Well, what's 1 minus 1? Divided by 2. So let's say we're trying, so for any node n other than the root, So we're saying find a node n other than the root. So let's say we want index 1, the left child of the root. We already know that. But just pretend we didn't know and it was somewhere random in the array. Then we'll say, okay, well, we want to find index 1, parent, index 1's parent. Then we'll plug it into the formula. 1 minus 1 divided by 2, and that equals to index 0, because 1 minus 1 becomes 0. 0 divided by 2 is 0. Now if it was index, we're looking for index 2, it would be 2 minus 1. Or if we're looking for index 2's parent, then we go 2 minus 1. That's 1. 1 divided by 2. In Java dividing, it's 0, so be careful. So if you, like I said, if you don't know, then go into your compiler or a secondary compiler and system.out.print the math, just the math. Do the math in there if you get confused on how to do math in code, because sometimes the dividing can throw you off. So just double check it. So after, hopefully you understand that, the formula, how to calculate where the nodes are stored. So that's how the nodes are stored in the tree. It's just in a linear fashion, and they all connect to a tree. So after that, we'll continue with the code. If I can just find that other notes that I have. Okay, so here we go. So we have, we'll do here the is empty. So we'll say returns true if this binary tree is empty, and false otherwise. So we'll say at return true if this binary tree is empty. And returns true, false otherwise. Sorry, returns true if this binary tree is empty and false otherwise. That's it. And here we'll have the method public boolean is empty, so returns a true or false. So return count is less than 0 or equal to 0, doesn't matter. I just do less than 0. Returns true because if it's less than 0, it's going to be empty. So returns true if count is equal to 0. Did I say less than? I think I usually do less than or equal to. So we'll say that count is less than or equal to 0. Returns true if count is less than or equal to 0. And we'll do the size. So this way it's easier. The array tree is easier. They have a count. We could have had a count for the linked implementation as well. That would have been a better idea. But they just wanted to do maybe a recursive example. So here we'll say returns the integer size of this binary tree. And we'll say at return the integer size of this binary tree. Then here we'll say public int size. We'll say return count. That's it. We'll have a contains. We have a find as well. And a toString, so just a few more things. So we'll do the probably do the contains. Actually no, why don't we do the find first? Then we'll go back up and do the contains. So we'll start with that. So here we'll do some doc returns a reference to the specified target element if it is found in this binary tree. Throws an element not found exception. So again, you're going to have all these classes if you follow this series in order. Starting with, what do we start with? The array stack. I think I have that back. I'll try to move that up or put these in a playlist. But I think the first video actually was the link stack. So if you have the link stack, you should have everything. you might want to do the array stack first, just in case, because that's where I might have made some of the exceptions. So arrays are actually a data structure too, they just don't really talk about them like that. So here we'll throw element not found exception if the specified target element is not found in the binary tree. We'll say at param target element, the element being sought in the tree. Here we'll say add return true if the element is in the tree. At throws, element not found exception if the element is not in the tree. So then now we'll do the public t find takes parameter t, so it takes a target element, so we'll say okay, our method is public t find, it takes a t target element as a parameter, and it throws element not found exception. Exception, whoops, yeah, that should be right. I don't want the brackets like that. So we'll say t 10 points to null, boolean found set to false. Then we'll have a loop here for int I is equal to 0, I is less than tree.length, because that's our array name. So tree is less than array, sorry, so this is a little bit of a different for loop, so we'll have I is less than tree.length, and we're not found, we're calling the method. What is not, sorry, so and found is equal to false, I believe, because if we say found, that means found is equal to true. If we're saying not found, that means found is equal to false. Excuse me, that's like a shortcut way to check a boolean. So here we'll say if tree of array of index I does not equal to null, then we'll say if target element dot equals tree of index I. Then we'll set found to true. Whoops, found equals to true, and then we'll set temp to point to tree of index I believe. Is that right? If? Yeah, that's right. So we can have an if statement like that. Whoops, and then another if statement below it. Then the condition, then the body. So if tree of index I does not equal to null, then instead of having a statement here like do this, we have another if saying, okay, well, if this is true, then check if this is true, then go into these statements here. So just some education on that. Then we'll do if not found. So if not found, after all that, we'll throw new element not found exception. And we'll pass in the array binary tree element not found exception in the array binary tree, so that's fine. Yeah, that's so just like that, nothing else. Actually, one more, just return temp to satisfy the t return type. That's it. That seems to be one of the biggest methods here. Then above that we'll do the contains. Actually, why don't we do it below, because I don't want to go back up. So here we'll say returns true if this tree contains an element that matches the specified target element, and false otherwise. We'll say at param target element, the element being sought in the tree. We'll say at return true if the element is in this tree. So here we'll have public boolean contains, takes parameter t target element. They're asking, okay, well, will this tree, does this tree contain the target element? And we're saying, okay, we'll create an object reference variable here. We'll create a boolean. We'll set it to false. We'll try. 10 points to find. We'll call the method find. We'll pass in our target element. We'll set found to true. Then we'll set, we'll do a catch. We'll call exception. Element not found exception. We'll set found to false. And return found. Should be right. Return found. Found is false. Catch exception. Try 10 points to find target element. Found points to true. Should be all right. Just check. I'll just check this find method again. So we have a t temp points to null. Found set to false. We're going to iterate through. So for int I is equal to 0, I is less than tree.length, and not found, I++, if tree of index I does not equal to null. So this on index 0 of the iteration. If tree of index I does not equal to null, if target element dot equals. So here we're going to use the dot equals. Is that what we used before? I believe it is. To check where equals compares objects. It's from the object class, indicates whether some other object is equal to this one. I believe it compares by memory location. We can test that out later. So we're saying if target element dot equals, so if the target, let's say we're looking for 5. If 5 dot so if we use dot equals, by the way, we can also compare strings and numbers. You could probably use equal signs here. That would just compare numbers. So if target element dot equals tree of index I, so if let's say we're looking for 5 and the target element at index 0 is holding 5, then we'll say found is true, and then we'll set temp point to tree of index I, so it just saves it as temp, saves the element, and returns the element. It points to that memory location, returns that memory location that we're looking for. That's it. So we've used this logic before. It just has a little bit of extra logic in the loop. We've done this before with the linked structures. We've used equals, all that. So if you're confused, just do trial and error. Say, okay, well, I'm looking for target element. So we're going to say, okay, if the target element dot equals the index I, which we are, what happened there? Which we are iterating through in our loop, then return true and return it. If not, we'll go back down here. We'll loop back up here, because this is like a connected for loop with no brackets, which makes it a little confusing, but I think it comes back up here. Then I will increment by 1. Then we'll say for int I is equal to 1, I is less than tree.length. Let's say tree.length is like 5 or 4 or something. Then we'll say, well, let's say it's 0, 1, 2. Let's say it's 3. So now we're at, let's say we have 5, 6, 11 in the tree. Then we'll say int I is equal to 1, I is less than 3, and not found, I++. If tree of index 1 is does not equal to null, then we'll say, okay, if target element, which is 5, let's say we're looking for 6, so let's say target element, so if 6 dot equals tree of index 1, which 6 is stored, then we'll found is equal to true. So hopefully you get the idea. It's nothing too hard. If you can grasp the equals method and the logic, it's just iterating through the tree, through the array, looking for the element. Here we have this toString I have here is asking for, well, what it's doing is going to do an in-order traversal. The in-order traversal, do we really want to print it out like that? I mean, we could, but we can do it another way too. So we're going to need to do a toString to get that object data out of the hash code. So we'll just say returns a string representation of this binary tree, showing the nodes in an in-order fashion. Actually, no, it's not going to be in an in-order fashion. That's all we'll do here. At return string representation of the binary tree. We'll say public string toString. We'll say string str points to that, empty quotes. Go use an iterator. We probably could. Could we try that? Actually, no, we cannot, because it's not a built-in. That's why we can make our own iterator, or we could just do this. We could do a for loop for int I is equal to 0, I is less than tree.length. I plus plus, and we'll say tree of index I. No, we could say tree of index I. No, we could say str points to tree of index I. No, str points to str plus tree of index I. Will this work? Plus a space. Space it out, it should. Then we'll say return str. Hopefully that would work. Or we could just use a method here called arrays.toString. So arrays.toString, we could pass in this. We need the java.util.arrays package for that. So we'll say arrays.toString. We could pass in tree, I believe, something like that. So we could do that as well if this didn't work. It should work though. But that's a secondary option if this one didn't work. So you could do that, you could do this, or you could use an iterator to print them out in a special way. So we may come back and do the iterator after. Iterator in order. We do have some in orders we could do. What does it in orders? We do have some iterators we could do. That's another hour in itself. Right now we're just going for the tree. We're just going for the tree itself. That stuff could be extra. So in our array heap, there should just be a few methods. We'll have an add element method, a little constructor that just calls super heapify add These methods are just a few lines, to be honest. Heapify removes has that branch of if and else. Otherwise, it's a pretty short code. It shouldn't take longer than half an hour. So I will come back and we'll do that.